John, do you have any opening remarks you'd like to make?
Oh, sure. One, I want to thank our 3 interns for putting this together. I'm really excited to see this. I was talking to Caleb at going away thing, and I got all excited about UX, UI, and he was showing me stuff on his phone. And I've been talking to Libby some and everybody, and so I'm really excited to see this, and I'm excited about the work, and just ready to jump into it. So that's about it. Thank you for everyone who's online, and it'll be a lot of fun. So.
So can I say something? Yeah. So I just want to say it's so great to have you guys this time. It's, the work you've done is fantastic. And just for the room in general, all of this work was funded by the Digital Transformation Office, except for Caleb's, which Skelton actually funded that one. That's kind of his.
You're welcome.
His sweet spot. And they're cooperating prototypes for each of the interns. So each one is kind of doing something that's some aspect of a smart campus work for the agency. And so the capabilities that they built this year will be used for further development on, so that we have some incremental products out of it. It's not just a go play and dabble kind of a thing. It's actually something that's contributing to the Smart Center activity at the agency. So we just want to thank y'all for that.
Right. Thanks, Dave.
Yep. Load up the charts.
Hey, don't forget to turn your mic on.
Oh, okay. There we go. All right. My name is Gabriel Johnson. I am a cybersecurity and computer science student over at Old Dominion University. And this time I worked with David Kelldorf, and I worked on the IoT devices in building 24 and 48 with Jeff Brandt over at Langley. Next slide. So my objectives for this internship were first and foremost to learn Grafana and PyVision. Those were the 2 systems that I used to work with this data. And then I needed to compare data between the 2. We were running into some interference with our Grafana data, and we needed to locate the source of that. And then once we corrected that issue, it was to validate the data to see if our fix worked. Next slide. All right. So first up, the first phase of this internship involved classifying the data. I spent the first couple of weeks learning how to use Grafana and PyVision, learning how to do C# and how to make queries between those 2 systems. After that, the data is pulled from paths. There's a path for each reading on the machines in those 2 buildings, 24 and 48. So I had to learn how to identify those paths that contain the interference on Grafana. After that, I pulled all of those paths in a list. There were about 1,500 between the 2 buildings. I pulled it on into Excel, and I went through each of those in a query in Grafana, and I searched each of them for interference. Next slide. So up here we have an example of that interference I was searching for. You can see the Grafana query in green and the PyVision query in blue. The PyVision is the known correct data in the Grafana. You can see that it follows that similar waveform over there, but it contains extra data. You can see kind of that smooth curve along the bottom side of those peaks there. And that is the interference we're looking to correct. All right, next slide. So after I figured out which of those paths actually had interference in them, I had to try to find the source of it. I started that by, again, comparing each of these in PyVision and Grafana. they both had the functionality to export CSV files. So I exported those, looked at paths that contained interference on Grafana, and then I looked at the data on PyVision, exported the CSV to Excel, and then I needed to isolate that interference pattern in the Grafana data and try to find a match for that in the PyVision data. I've got an example of that coming up next. Next slide. So I did, for this searching for the interference, it was more manageable to work with about a 10-hour window. So that's about what I worked for with my exports from Grafana. I would take those 10-hour windows, and you can see the normal data over on the top of the graph, and then that kind of smooth curve effect down there on the bottom, that's the interference data. So I would use filters in Excel to isolate that data and then search for it in the PyVision data. If you go to the next slide, we can see that's the data after it was isolated using the filters in Excel. Next slide. After that, I would take that isolated data, and it would be in a list of points I would take, and I would export the PyVision data. Where I had a 10-hour window in Grafana, I would go about 12 hours on each side of that data from the PyVision, because we suspected it was a time-based interference with time zones. So I was going to search to see if I could find possibly repetition of that pattern within the PyVision data in either forwards or backwards in time.
Did you find one repetition?
I did not. Get into that, you're ruining the story. But so we went forwards and backwards in time with that, about 12 hours on each side, and I learned how to use advanced filters in Excel, took that list of points, filtered the PyVision data. It was usually about 100,000 points per, I guess that would be a 34-hour window. And I would filter it down. You get about probably 30,000 points at the end of it, just from matching the range of points I got from the interference pattern. And then I would search through those and graph them and see if I could find any similar forms to match the interference. You can see down there on the right, it was kind of a match to that interference pattern we had before, and I came up with this a few times where we would come up with a match that looked kind of similar, but the time scale was completely wrong. It was usually a 10-hour interference from before, but this happened over about 10 minutes, so it turned out that was not the cause of the issue. So if we go on to the next slide, we decided it might be something even further with a time range. So that 34-hour window didn't produce satisfactory results, as we spoiled earlier. So we expanded it up to 2 months on each side instead of 12 hours on each side. So I exported that into the CSV into Excel, did the advanced filtering technique on that again, search for a pattern in that. You can see an example of this is the series that I used for that 4-month study there, where the bold lines on the top and bottom there are the correct data from PyVision. And you can see, again, it's got kind of a smooth curve characteristic to it in that dome shape going up and down there. I tried a visual search as well on PyVision. So not just the raw data, I would go with the visual. I would start at the 2 months ahead of time, set my search window to about 18 hours, and then went through the entire 4 to 5 month range with an 18-hour search window, seeing if I could find any repetition of this kind of smooth curve pattern here. And there was none. It was all very jagged data, or had like a square wave type form to it. So we were pretty successfully able to rule out time-based interference based on that once we went that far of a time range. Next slide. So we ruled out the time-based interference, so we had to search for possible other issues there. And what we ended up finding is there were, in some of the paths, there was a component missing from the path. So the path structure usually went something like you'd have the building number and then say the machine name and then the component associated with that machine. And some of them had the structure of the building number and then it will skip straight to the component or some variation of that. So we went back to the C# code Jeff did, and he corrected a source of that there, and we remapped the paths to new test paths. And after that, we had, whereas it was about 1,500 paths between the two buildings before, we ended up with about, I think, 3,000 or 2,400 paths after that. So we definitely got a lot more data. And what it seemed like it was doing was taking the data out of multiple of those paths together, combining it, and that's where we would get that interference from. So after we fixed those paths, it seems like it separated it out pretty good. If you go to the next slide. So after we implemented that fix, you can see there, that's one of the series that I graphed out between the PyVision and Grafana there, and you can see it matches up pretty well. It's not the exact same because the time range is a little bit different on them, but you can see the waveform doesn't have any more of those like smooth sloping issues with it or any of that interference with extra data added on to it. So after this point, it was up to data validation. We've implemented the fix. Now we're making sure that it works. I've tested out on several fields so far, several of those paths between the Grafana and PyVision, implementing those same methods where take them, export them to CSV, and then search for any type of differences between the PyVision and Grafana. And so far, it looks like our fix has worked pretty well. It looks like we've got it working. If we hit the next slide. So our next steps now are where I've been doing kind of a concentrated study on smaller time ranges. We want to expand it kind of into a multi-month time range like we did before to rule out that time-based interference and get some a larger sample size to definitely say that this is working and we're good to go. After we hit that point, then we'll be able to use Grafana, use the IoT data in the cloud, and we will be good to make good dashboards in that. All right. Any questions or comments? It was. I crashed Excel more times than I've ever crashed it in this one semester.
Very important to get the data right, so your analytics, you can trust your analytics.
Yeah.
Right. I've done that.
Very solid.
Online have any questions?
Code.
This is Jeff Brandt. I had a comment. I just wanted to say, I think we all understand that data quality is really the cornerstone of trust in any information system, and the work done that was presented here has really gone a long way to root out a very difficult data issue we have had with our getting our facility operations data into our IoT platform, which is really essential for a lot of these forward-looking smart center applications. So really just hats off, great work here. Thank you.
So how clean, I'm going to use a word that probably doesn't make any sense, but how clean is the data, would you say right now? Just guessing from a validation standpoint.
Yeah, so on small time ranges, we've seen that it's a spot on. Really what we want to
cool.
do is select large scale aggregates. So take a measurement, say what is the total of every single 1 second measurement for this particular sensor over the course of a year, and figure out what that sum is and compare it to both systems. So doing large scale measurements like that, we can make sure we're spot on, but that's really our goal, is 100% accuracy.
Awesome. Okay.
Looks like we got a hand up, Rodney.
Yeah, I'd like to echo Jeff's comments. Really great work. It's, I think, a good experience to actually get at the sort of Pareto principle about the 80-20 rule. 80% of your work is really going to be in what you've done here, and that's making sure that the data that one has to work with has veracity, and this sort of detective work is absolutely necessary. Technically, I did have a couple of questions. First being sort of the nature of the filtering that you conducted when you were looking for time-based interference. Did you have any indication that this sort of well, first of all, how were you aware of the fact that it was interference? Was it just based upon sort of qualitative inspection of the trace, or was it just kind of built-in information that was provided to you when you gained access to the data?
So the way it looked like interference was because if you looked at those graphs where I showed it before, at least though I didn't put many examples in the slides, but in Grafana where there was interference, you would have the series from PyVision, the known correct data, and then there would just be additional data on top of that. So that's where we determined that there was some kind of source of interference adding on to it, because you had the data points that matched up, and then you had extra stuff in there on top of it.
Okay, so it does sound like it was sort of a visual, qualitative means by which you were able to very successfully identify that it was some sort of interference. I guess the follow-up question is, okay, based upon using your own interpretation of that, do you know if there will be any way to actually develop some sort of algorithmic way to automatically identify, hey, this is what it is, it's interference, and here's a way to present the means by which you can extract that or remove it somehow?
I haven't thought of a way to automate that, but we were able to find that source with the path issue, and it seems like we fixed it. I'm not sure if there was another type of interference. You could probably develop a program to detect that, but I don't have any experience in that area.
All right. Thank you so much. Appreciate the great work here.
Anyone else have any questions or comments?
Just the dogged determination to go through that is impressive.
That's a lot of detail.
Yeah. One of the nice things about this is once he gets done with this will be agency information that all teams can access now and have some confidence that, that the data is accurate. So that, do it once and not, silos.
Go Excel. Yeah.
Yeah. Not Excel in here.
Next, tell us about what she's been doing. Okay. This chair. The camera will focus on you then.
Baby.
Hello, maybe.
Being slow today.
Well, they had some substantially large file sizes.
Oh, yeah.
All of this,
I made mine smaller.
you rocked it.
So while this is pulling up, let me also just special thanks to Jeff Brandt, who is just the subject matter expert for this whole area and has been invaluable for all three interns really to be able to answer, and help investigate these issues.
Thanks, Dave. It's been my pleasure, and I really appreciate the intern support.
So that's fine. Okay.
So hi everyone, my name is Libby Lewis. I'm currently a master's student at Johns Hopkins University in the computer science program. And I've been working with Dave Kelldorf and the other interns on our project for this semester. Next slide. Okay.
You have one of each.
That's okay.
Yeah.
Oh, okay, so this is kind of like an overview of our IoT Holographics project. So currently there are IoT sensors on the machines in buildings 24 and 48 on JSC's campus. So the first part was what Gabriel talked about, ensuring like the data's the integrity of the data when it's stored in the cloud. And then my part is performing predictive maintenance machine learning on the sensor data. And then the part that Caleb will be talking about is using that sensor data in augmented reality using the HoloLens. So so what is predictive maintenance? Predictive maintenance is trying to predict when machines are going to fail or break down, and that way you can save money, time, parts, labor by trying to know what's going to happen in advance. So there's different types to it. It involves machine learning, which is a form of artificial intelligence. So there's supervised learning, where you have labels to your data. So you can do something called regression, where you're trying to predict the time to failure. So how much time is it going to take from this point to when it might fail? Or you can do classification, where you have like a given time window, like say the next 2 days. Is it going to fail within the next 2 days, yes or no? And then you try to predict that binary classification. You can also do multi-class classification, where you predict, is it going to fail in 2 days, 3 days, 4 days, something along those lines, or the type of failure. There's also something called anomaly detection, where you can try to detect, is this sensor giving like something like data that indicates that it's not like a normal behavior that's happening right now. So all this can be really useful in planning maintenance schedules and doing preventative maintenance. So that way the machines will last longer and you can save time and money, as I said. And it's also will eventually be useful for like a lunar base, where you have parts and time are very limited there. So you want to be able to use all the resources you can in order to prevent having things break down unexpectedly. So next slide. So the machine learning tools I used for this semester were mainly Vertex AI, which is by Google. So I used the datasets were stored in BigQuery, which is their database platform that they use, and then also in Google Buckets when I uploaded my own databases. There's also, they have a thing called AutoML, which basically takes through and runs through different algorithms for you. And so it's kind of tries to optimize it. And then you can also create your own custom models using your own code. So there's kind of two options for if you want to do less coding or try to do more of the tuning yourself through coding. I also use Kubeflow a little bit. So that is similar in terms of a platform that you can code on your own machine learning and run models. And both of these can scale really well to larger data sets as well. I also use a little bit of Colab, and all this is under the AppDet account for NASA security. Next slide. So the facilities data itself, it measures vibrational data, so velocity, acceleration, motor speed of the assets. And those assets are like the chilled water pumps at JSC, cooling towers, chillers, condensed water pumps, all the things that keep JSC cool. And the historical sensor data actually goes back several years, and there's also work order logs for the machine maintenance that date back to 2008. So you have a lot of data about when the machines actually broke down. Next slide. So in order to create a data set, in order to run machine learning, you need data first. So I use the PyVision website that Gabriel talked about a bit to visualize and export the data. I focused on just the chilled water pump 2, just picked one for this, but this process can be repeated for any of the assets. And then you can use it for just basically create a model for any of the assets if you get the data for that asset. So I used the data from January 1st to June 30th from 2021. There were 2 failures during that time period, so I thought that would be a good amount of data. And unfortunately, the way you export it, you can only export about an hour of data at a time. So it took a while to create 6 months worth of data. But I created a Python script that combined all those files and made it a lot easier than just copy pasting everything. So basically put it into a format that I can use for machine learning, where each entry is a date time stamp, and then the columns are the vibrational measurements, different types. For example, here, the motor drive end axial velocity. So the drive end of the motor, the velocity in the axial direction is what that's measuring. So next slide. So cleaning the data, the data points are actually taken anywhere from 10 seconds apart to 15 minutes apart, and that's kind of hard to do a lot of forecasting with the different machine learning models, since it's different intervals of data points. So I standardized them to 1 minute intervals and use like the mean. If there were multiple points within that minute, then I used the mean of that. And then there are also some gaps where there were minutes where there weren't any data. So I use linear interpolation to fill those in, and that's kind of what you can see here with the graph where I was able to fill it in and then bucket it into 1 minute time intervals. Next slide. Also with bucketing the data, you can use different intervals for the buckets. So on the far left, you can see the original, and then the 1 minute bucketing in the middle, and then 5 minutes. On the bottom are 10 and 15-minute intervals. And as you see, when you get up to 10 and 15 minutes, you kind of start to lose shape of the graph. So it is advantageous to use bigger intervals because you have less data. But then you can also you have more data, or sorry, when you have less data when it has bigger intervals, but then you start to lose the shape of the graph. So basically up to about 5 minutes is probably the best amount of largest amount of bucketing you could do, but I ended up using 1 minute time intervals for my project. Next slide. So exploring the features as well. These two features I ended up not including, the features being the different vibrational measurements. So I didn't end up using these because their data ended up dropping at the end of February. So they're missing a lot of data. You can't really impute those missing values once it gets to that point because there's just no data to go off of. And then also there were features like building number, and that's just not going to change between the different timestamps. So those are also dropped. Next slide. So I first tried a classification model. Actually, I tried an autoregressor first, which basically tries to forecast taking a vibrational measurement like the velocity in the axial direction, tries to predict the next one, but it was very inaccurate. So I tried using Vertex AI's AutoML forecasting. So that basically just tries to predict the next vibrational data point. And then eventually you can kind of use that to see if the machine is failing based on seeing what the next data point is going to be. Unfortunately, that also didn't give great results. And I also found out that the AutoML forecasting, you can't do online predictions with that. And online predictions are necessary if you want to do real-time predictions from the model that you created. So I ended up going with the classification where I manually labeled the data based on the work order. So for instance, there was a time period from February 10th to February 27th in 2021 where the machine was broken. So I labeled all those data points as broken, as a 1, and then everything else is a 0 where it wasn't broken. And basically sent that through to see if it can predict, okay, is it broken or not at this point? And then there was also failure sometime in June, so then I used that in the testing set to see, okay, can it predict, is this going to be broken at this time point? Next slide. So the results of that, I used Google's AutoML classification for this to start out. Ultimately, the results look great, but unfortunately, the very high, the F1 score is very high and precision recall are very high. But unfortunately, there's only 2 instances of failures in here, and it's very easy to get great metrics when the data set's unbalanced. So it looks great, but it actually, the real meaning behind it isn't fantastic. So unfortunately, it's also difficult to determine when exactly within these time points the machine failed, considering that you're looking at, it was logged on February 10th, but it may have failed 2 days before and no one noticed. And it may have been fixed on the 27th, but they may have put in the work order late, and there's no exact timestamps for those. So there's a little bit of discrepancy in the data in order to really be able to use this method well. But next slide. However, I really wanted to actually, come up with a real-time prediction pipeline. And once you come up with this pipeline, you can pretty much trade out what model you're using, and then it'll work for any of them. So I went ahead and used classification model, even though it wasn't the greatest model in the world. And so I set this up where you're taking the MQTT input of the real-time sensor data from the machines, transform it into the correct format for the prediction request. You go through a Google authentication using a bearer token, then you send an HTTP request to the deployed model. You deploy the model on Vertex AI, that's where it's hosted. And then that sends back the results of the classification running the prediction. And then you send that to the MQTT topic, and then that gets displayed in Grafana. So you go to the next slide. So this was all done using Node-RED server. So you can see on the top, that's kind of a sample of what the pipeline looked like. That's actually a manual version where I typed in what the input was I wanted to send to it. I did end up creating a version where it actually takes the real-time data and sends it in, but there's been an issue with the connecting the input to it. So that hasn't quite gotten working yet, but I know the structure, the rest of it works. So this pipeline does send data to the model and then sends it back. And then the bottom is the graph resulting in Grafana when you send the request, and then it sends and comes back with prediction 1 here saying that it was broken. So the goal eventually is to display this real time on the HoloLens, but have to figure out the input issue first with that. Next slide. And then last thing I've been trying most recently is determining an anomaly detection model. So this is using Vertex AI's custom model where I'm doing the code myself. So you're basically trying to predict an anomalous vibration reading before it happens, and then you can say, oh, the machine's going to break soon. Then you can go do something about it. So I used an iForest model to predict the anomalies. If you look, this is a lot of graphs, but if you look on the very bottom, the red graph, second from the bottom, that shows either a 0 or a 1, 1 being predicted to be an anomaly, 0 being not. So you can see that cluster of red kind of just off center, close to the center. That actually is when the machine was broken in February. So that corresponds to about the February 10th to the 27th. Then when the machine was restarted and you see that whole vibration all the way up and all the different graphs, that was when the machine was restarted after it was fixed, and then it is fine after that. So it is actually kind of showing when there were issues happening with the machine. Whether or not this would be predicted early enough, that's still to be determined. And I definitely want to work more in kind of in the next 2 weeks of the internship, still try to move forward with this model and try to do more with it. So next slide. So just a few challenges of this, kind of talked about some of these already, but basically a lot of predictive maintenance uses a life cycle of machine, but that data isn't really available at this point, or at least not that I had access to this semester. And there's also a lot of times detailed log events, like exact timestamps when there was a failure recorded or a fix was done. And there's also needs to be a differentiation between anomalies, and usually when the machine starts up, it spikes in vibration, but those are normal. So an event log for startups, I wasn't able to have that, and so it's hard to tell when it may have just been a startup event versus an actual anomaly when the machine was breaking. Another thing, like I said, the immediate pull of data from the sensors during real time is not currently working for the input, so there needs to be some figuring out how to fix that. And then also looking at Kubeflow, I tried doing a little bit with that, but it currently doesn't have support for online predictions, and you need that to do real-time predicting. And when you try to do it on there, it's hosted on Google Cloud anyway, so that's what Vertex AI does itself. So right now, Vertex AI seems to be the better option for hosting a model and doing real-time predictions. Next slide. In future steps with this, in the next 2 weeks before the internship ends, I'm hoping to keep working on the anomaly detection and actually deploying the custom model in Vertex AI. And then you can also export custom models from Vertex AI to Kubeflow. So I can try to compare between those, how it runs on Vertex versus Kubeflow. AutoML models can't do that. That's why I haven't done that yet at this point. And I also want to compile the lessons learned for any future work that happens. But future work where this can go, in terms of this work, I think it would be really great to work with center ops more directly in order to tailor the ML model more to their needs. And then also trying to deploy it on the HoloLens, trying to track some of the things more and experiment more with Kubeflow, and then also tuning the anomaly detection model and trying different algorithms. And again, this can eventually be used as a use case for something with the lunar or Mars base. Next slide. So that's the main project I worked on. I threw in a couple of side projects that I've also been working on for this semester as well, in side and main projects as well. But this is the MTDS project, the Mission Telemetry Data Services project I started out with. It's basically was used for me to get familiar with Vertex AI and BigQuery. So that it's trying to predict when the KU band on ISS will shut down by looking at different temperatures. So I used the Vertex AI AutoML forecasting model to try to predict the temperature. Mainly that was just trying to get used to what Vertex AI does, how it works, how to move forward with all that. Next slide. I also joined a team that is working on a project called Iris, which is a voice assistant for astronauts. So right now they're working on an NBL use case where they are working on the evaluation. They have an automatic speech recognition engine, which basically takes the audio recordings from the NBL and transform it into a text file. And so right now they're trying to evaluate. They had a group go and train this on the NBL recordings, and they're trying to determine, okay, is this actually working well? So I had to research evaluation metrics. A lot of times use word error rate, how many words did it get wrong, what percentage, stuff like that. I also created a manual transcription of an hour-long NBL video for a reference transcript. You need a reference transcript in order to see how well the engine is working itself. And then I also worked on a command line product to be able to run these evaluation metrics. And you also have to do some pre-processing and things with Python as well in order to make sure that the transcript that you've typed out and the transcript that it's producing have like the same normalization, like they're all spelling out the numbers, they're spelling out contractions, things like that. Also, a fun fact, that is my own photo. I got to tour the NBL and see astronauts waving to us while she was going down. So, so very fun. Next slide. And then I also got to do work on the DO survey analysis. So the Dare Unite Explore survey produced a lot of free-form text responses in response to products we can improve, processes, and facilities. So I used natural language processing techniques in order to analyze the results. So the results are split into 3 different groups: tech orgs, mission support orgs, and programs orgs. And then for each of those, each of the questions I determined the most common 1-word, 2-word, and 3-word clusters for each question. So for example, on the right here, you see a graph where it produced, this is a question, what products do we need to improve most for the tech orgs? And you can see that the words collaboration software appear together the most. So a lot of times that means like they want to do more collaboration software that needs more work or something along those lines. And these were kind of able to inform themes for the future center commitments moving forward with that. Next slide. And I created a methodology page for this, kind of one pager about what I'd done with this. And then this was working with Dr. Goodwin. She was generous enough to be able to let me be a part of this and then also be able to participate with some of the senior staff workshops too, which was an incredible experience. So moving, next slide. So that's all the technical stuff. I thought I'd throw in a few of the fun highlight things I got to do as well. So I got to tour mission control, which was so awesome, amazing, so many chills. And then I also got to meet Gene Krantz and hear him give a speech to the interns, which was really fun. Top right is only loosely related to NASA, but I went to the Wings Over Houston air show and got to meet the Blue Angels, which was really cool to see them perform and meet them. So and then bottom middle is the Artemis launch a few days ago. Went to the Space Center Houston launch party and then got to tour Chapea, the bottom right, where they're going to have people living for a while, being able to test living on Mars and stuff like that. So next slide. I also went on a vacuum chamber tour where I got to see where people live and work in different vacuum chambers that they test things in at the center. And we actually got to go into the vacuum chamber A, which was really cool. I don't have any pictures of me inside since it's a clean room, but yeah, that was really, really amazing to be able to experience that too. And next slide. And then I also was fortunate enough, I won one of the car passes to go see the Crew 5 launch in Florida. So I flew out there and got to see Crew 5 launch, see the Falcon 9 launch, and I got to tour Kennedy Space Center when I was there too, and see the space shuttle and everything. So that was very cool, and I'm very grateful I got to do that. Next slide. So final wrapping up, this future, I'm returning to my hometown, Peoria, Illinois for winter break, and I'll be finishing my master's in computer science in the spring. I'm doing concentration in bioinformatics as well. And so just working has really renewed my passion for the intersection of science and technology. And I know I've learned so many skills here and lessons, and I'll be able to continue working on those for cutting edge projects. And also NASA just really maintains a level of excellence that you do the impossible here. And so I plan to pursue all my work with that same passion in the future. And next slide. So that's it. I just want to say thank you so much to everyone, especially Mentor Dave and Dr. Goodwin for just everything, anyone who's helped me here. It's been such an incredible opportunity and I'm so thankful for all of it. So thank you all very much. If you have any questions, I can answer them too.
Any questions for anyone online? Probably somebody. A nice comment. Yeah, we all want your life.
I just want to say too, Libby has done something that I was really happy about, and that is to pick up a model that somebody had previously created and was able to find it, pick it up, use it, tweak it, and, you know, reuse it. And I think that's an important part of what we're trying to get to. That was good.
Very cool. So much, Libby. Okay. So,
I've got a question
you have a
from
question? Okay,
online.
go ahead.
Yeah, this is Scott Brown's Libby. You had a variety of different projects that you were working on there, and it kind of spanned a whole lot of different things. I'm just curious, did you have a favorite of all those things that you worked on?
They were all so different. So I don't know. Being able to work on the machine learning was really fun. Just kind of, just kind of go and just explore and see what I can do with it. I enjoyed the do survey just because that was different than some of the things I've done as much, and it was both technical and more of the analysis of being able to look and see where JSC is headed in the future and learn more about that too as well. So yeah, I enjoy doing the machine learning part of it too, though. That part's really fun.
Cool. Yeah, I mean, very impressive different sets of things that you were looking at. They were related, but quite a variety there. So good experience that you got.
Yeah. Yeah, I really enjoy working on a lot of different things. So it's fun to be able to pop into different things and contribute to all of them.
And
Rodney?
Rodney Martin.
Yeah,
Rodney
I
Martin.
thank you for the this talk. It was fantastic. I'm surprised you were able to squeeze all of the work that you did and experience with and exposure to different projects in the span of just one session. It's very, very impressive. I did have a question on the first part of your work that you reported out on your machine learning, and you're exploring a variety of different techniques for essentially trying to determine the onset of a potential failure or fault of some sort. And I think you were looking at regression, classification, like binary classification and multi-class classification. And ultimately, it seemed like you came to the conclusion that the classification, while it wasn't ideal in terms of performance, was the one that you converged on. And I was also impressed at seeing the kind of array of different metrics for binary classification, including ROC curve and area under the ROC curve, which is has less of a sensitivity to class imbalance as some of those other metrics did, but you still need a sufficient sample from each of those populations. My question is, what do you think the problem was with the regression that caused just a really poor accuracy, even less so than for the classification?
Mhm. Yeah, I think part of it, I think, was the difficulty with the regression of being able to, find a time to failure, and that is very difficult when you don't actually know when exactly the failure happened. And I think that was maybe, the label may have not been entirely correct in order to be able to determine like the time difference, just because the data, it may not actually match up with what was happening in the data based on the labeling that I had. So that was one thought. It could have also been just some of the parameters I was using. I wasn't as familiar with the particular regressor that I was trying to use. So that would be something it would have required a lot more research, I think, for me to dive into it and to really learn more about that, I think, in order to really try to make it more robust. And I think I wanted to move forward and try some other things first. So given more time, I would probably circle back around to it and try. But I think time frame wise, I think it was the classification was easier to move forward with more quickly.
Great, thank you. Outstanding work.
So we're getting kind of close on time, but now we have Caleb ready to present, I hope. So we'll get his chart showed up here in just a second.
Okay, okay. All right. Hope y'all can hear me all good. Howdy. All righty. So doing the HoloLens stuff, I want to kind of focus on one major thing that's really focusing on this project, which is spatial anchoring within this project. And that's basically being able to have this HoloLens device understand where you are in the real world, reference that to the cloud, and then give you information related to that. Because I'll get more into it later, but basically the system used to use QR code scanning, and we're trying to get rid of that. So you can just have persistent data based on your location. You can head on to the next slide.
That was your phase A, was the QR code.
Back when we thought that was cool.
Well, honestly, I mean, the QR code is still cool. It's just like there's ways you can do it without it now, which is nice. So, yeah, so this is like a little chart that kind of shows how the data moves in the original layout of the system. And it's a lot to look at, but essentially the HoloLens scans the QR code, and then it asked MQTT, it goes, hey, here's this QR code. I've got a little ID in here that relates to a certain machine. Give me the data that relates to this ID. It's essentially all you need to know out of that. This is a big chart that shows that, but that's kind of the gist of it. And once it gets the data, then it drops the numbers from the sensor, and that's pretty much what was set up. Our goal is to replace that QR code with just a persistent display based on where you are in the real world. So we can get on the next slide. And so this is being done with spatial anchoring from Azure Spatial Anchors built by Microsoft. So the way it works is that you can create an anchor based off your spatial mesh. So the HoloLens can basically create a mesh of the environment, it sends that to the Azure cloud, creates an anchor ID for that. And then you can close the application if you want, or have another person enter that application on a different device. And when they go in, it will basically look at the cloud anchor and then reference that to their current environment. And if it matches, then you can basically give them virtual content based off of that. So you can create an anchor, get an anchor, and then place virtual content based off that anchor. So you can head on to the next slide there. Now, so how the content is placed. This is done by having basically like a anchor in that environment and then having things that you previously have set. So in this specific use case, what we're doing is that we would have a spatial map of like B24 or B48, wherever the data is coming from. And then the anchors are tied to specific endpoints in MQTT. So it used to be that a QR code was tied to a certain endpoint. Now we're tying the anchor to a certain endpoint. And then based off that anchor, now we can just have all the data display in relation to that in the real world space. I wanted to have a video showing this, but I couldn't get into the building to actually show it. So I ended up kind of changing gears yesterday and making a bunch of demos that just showcase how Azure Spatial Anchors works. So you all kind of know what can be done with it. So if you head on to the next slide. Okay, so these are a couple demos I built. These are things that I built for myself to learn how Azure Anchors works and the limitations of it. And then yesterday I polished them up so that I can show them to you guys. The first one is advanced controls for Azure Spatial Anchors. This works on Android and iOS as well as the HoloLens. And specifically, this is going really in depth. I'll go over all the buttons that are in it later, but you can control every single aspect of the anchor, where you're saving it, how you're saving it, how you're passing it. And then I made another one that's much simpler, where all it has is save and load, and that's it. It's not very complex, but it's multiplayer supported. So you can have a lot of different people in there all together at the same time, which is fun. And then I've got a cross-platform version just to see if I can get it working on a bunch of different devices. And through OpenXR, I was able to get that working on a whole lot of stuff like a Quest VR headset, as well as the HoloLens and like phones. And then I've got the last one is a world locking tool, which is really fun. And that one, that'll make more sense once I show it. But it combines spatial mapping of the environment with the with the anchors to basically try and place as many anchors as possible and see what the limits are there. Yeah, we can head on to the next slide. All right, so the advanced controls for Azure Spatial Anchors. You can see all those buttons over there. Unfortunately, you can't really read them very well, but I have a list of them there, and that's every single one of those controls an aspect of the anchor. So you can start the session, end the session. You can create an anchor, remove the local version of that anchor, and then find it from the cloud and pull it back into your real world space. You can delete the cloud version of it. You can anchor it to your local disk. You can anchor it to the cloud. There's a lot of options. This got really complex, but this is where I kind of learned the limits of like how you can interact with Azure Spatial Anchors, because there's a lot more there than I realized. But yeah, and I've got a little video of this. If you click on the little link at the bottom, yeah, it should open up a YouTube video. You don't necessarily have to watch the whole thing. I just wanted to have a video that kind of shows. Bug window over here that lets us know things are working as expected. Yeah, I don't know if you'll be able to hear my narration or not. It's not super loud, but
anchorable table right now. Right now it's not anchored.
Basically that table is the anchor, and so wherever I save that, it'll anchor it back and forth. And then I've got all the controls here. And in this video, I basically just run through all of the sets of each button, and I've got the debug log there telling me when anchors were created, when they're saved, when they're deleted, all that fun stuff.
Explode it out. Oh, yes.
The table is the anchor.
Yep, yeah, the table is the anchor. Yeah, specifically that blue part of the table on the bottom, that's the anchor portion. Yeah. So wherever I move that, if I like remove the local one and then restore it from the cloud, it should pop it back there.
So we've got start your session.
Yeah.
So we'll go ahead and start the session real quick.
It's kind of fun.
As we're connected to Wi-Fi, this should work. All right.
Well, your data center written all over it, doesn't
it? It's fun. It's fun.
And
Yeah, we don't.
If anyone walking into the room with another headset, they could come in and interact with that.
So with this one, no, but with the next one, yes.
Okay.
Yeah. Oh, well, okay. Okay. So someone else could load their own version of the experience, and as they could pull the cloud anchor, yes. But they wouldn't both see the same thing at the same time. Necessarily. They'd see the same anchor, but not the same experience. Their local versions would be different. The next thing I'm showing, their local versions are the same. And so everyone sees the same thing no matter what device they're on. But yeah, if we want, we can go and move on from here. This is basically just kind of going through all the buttons to make sure they actually work. And kind of showcase that.
Is this Caleb's YouTube channel?
Oh, yeah, yep,
Yeah,
yeah, that's me. So we can go and head on to the next slide. All right, so this is the multiplayer version of that. It's basically the same experience, but the controls are much simpler. The cool part about this, I added spatial occlusion because the way I did multiplayer, and so that means that in the HoloLens, if someone walks in front of me, it will do its best to occlude the hologram with them in front of it. So it knows like, hey, here's the hologram, here's the person. It'll block out that part of the hologram with their outline. And so like, it looks a little weird, but you'll see it in the video. It kind of is trying to keep track of the environment and people in it. But yeah, same kind of thing. We can go and pull up the video if we want. This is real simple. It just has a load anchor, save anchor. You can toggle the spatial mesh on and off. And if you want, you can unlock the anchor so you can move it and then reload it from the cloud. Yeah, and so, and this one's nice. The multiplayer part of it makes it really fun. I didn't have a multiplayer video, unfortunately, but I've worked with projects similar to this before, and it's a lot of fun to play with because you can see people's interactions with the same thing. So this is all loading up right now. So when that popped onto the table, that meant that I'm connected to the network. You can see it's trying to occlude because of the people in front of me. It's not perfect, but it's doing its best.
yeah.
It's getting there. And right here, if I remember, I think I had a hard time with the hand tracking. Yeah, that's right. Jump like. Okay, we'll wait. Basically, what I'm going to do is I'm going to move the table, create an anchor, move the table again, and then move it back to that anchor spot. And all that stuff, the cloud. So that's the little hand menu. And so right there, I'm creating an anchor. I was in the process of editing these videos to make them shorter. Okay, got it. All right, yeah. All right, cool. So that creates the anchor. And then now the anchor's created, I can unlock the anchor, move it somewhere else. Then I should be able to load the anchor and it'll move it back to the original spot.
You're just sitting here with your headset on.
Yeah. So we had intern photos for the headshot photos, and like this was yesterday, and like I'd gotten the demo running. It's like I got to get a video, so I'm just gonna do it while I'm waiting. But yeah. Yeah, I know, right? Yeah, so it moved it back to the original spot, and yeah, that's off the cloud. That's all anchoring. Yeah, we can go and head back to presentation. Well, that gets the coin across, but
All from the cloud.
yep,
Yeah.
yep. Yeah, Azure Cloud Services, pretty cool. We can head on to the next if you want. Okay, yeah, so this was a cross-platform attempt, and so one of the things I did was I integrated Mixed Reality Toolkit, which is what we use for the hand interactions, with OpenXR, which is what most AR/VR headsets use as their standard for interactions. And once I got that integrated, that allows us to build this project, which is very simple. All it does is stop and start an Azure session, but it allowed me to build that to any device, like any AR/VR headset, any like phone, tablet, whatever. And so that's pretty cool. I didn't even know that was going to work. I just kind of tried it and it did. So that was neat. We can head on to the next slide. This was really fun. I got this working, I think at like 4 or 5 p.m. yesterday, and it was mind blowing to me, at least when I got it going. There's a lot there on the screen. Long story short, you can control a lot of aspects of anchors. And the reason I built this was to see how many anchors I could make in an experience before it broke. And the answer is I got to 580 and then gave up trying to break it. The way that this works is it drops an anchor roughly every 5 to 10 feet that you walk. puts that in the cloud, and then each anchor has a piece of the mesh attached to it. And so you can delete your location and then go back to it, and it'll show it like, hey, we recognize this mesh. We look at the cloud, there's the mesh, here's the anchors attached to it. So we can go ahead and click on the title there, and that'll take us to a video. And then I'll have you skip to like the last, like, go ahead and skip to like 16 or 17 in the video. A little further. Yeah, try that. I was editing this video and it didn't export in time, so we have the uncut version. All right, so you can, this visual, so this showcases the map that's being collected at runtime and being saved to the cloud. So that little mesh thing you see in my view, that's what's being saved to the anchor in the cloud. And then all the little green dots on the floor, those are the actual anchors that are saved in Azure Spatial Anchors.
Okay, so it's following you when you go.
Yeah, and right now it's like a little thing where I just kind of shoot like a little pill capsule thing and it just kind of tests to make sure it's actually anchoring the environment.
I'm actually testing a thing for my project. I'm supposed to
Yeah, I
present
missed it
tomorrow.
too when he was walking over to the building. It was creating anchors on the sidewalk. The whole time he was walking, it was mashing out his world.
Yeah, if we watch this whole video, I went all the way from building 45 to building 2 and mapped the whole thing and made just under 500 anchors, and it tracked the whole thing seamlessly. And then I was able to close the app to like basically remove all local anchors, close the app, reopen it, pull them from the cloud, and then it popped back in an environment where I'd left them. So that's where this gets interesting. So you can have persistent things. Like right here, I removed all the local anchors and I'm loading them back from the cloud. And so those just popped back in from Azure right there.
That's quick.
Yeah, it's pretty quick.
And
And
it was
then
on the wireless.
I have a mobile hotspot running this. Yeah.
Curious.
Yeah. I've got a mobile hotspot on this one just because that's an easier workaround. And it's like right here, I close the app, reopen it from scratch, and I'm gonna pull the anchors from the cloud again. It's like right there, that's the load button. And there we go. Yeah, if you hear the audio, I'm celebrating. I didn't think that was gonna work. I was like, wait. Like I just loaded how many anchors? Like but yeah, that's kind of the gist of it. We can head on back to the presentation.
See the fingers.
Yeah, finger soccer. Yeah, go to my YouTube channel for finger soccer. But yeah, I think that's all I have. We can head on the next slide if we want. I just want to say thanks. This has been a really fun project. It's given me a reason to do a deep dive into spatial anchors. Like I've been playing with spatial anchors a little bit on the sideline for like a year now, but I've never really gone deep into it. And so it's nice to have an actual reason to like, all right, dive deep, figure out the limits. It's been a lot of fun to learn about it. It's been a lot more capable than I expected, to be honest. But yeah, I gotta give a massive thanks to David for this opportunity and huge thanks to Jeff. Jeff is like one of those people that just knows a little bit about literally everything. And he's been a huge resource where I could bring any question to him and he's got some useful feedback on it. And so it's been an awesome project. I've loved it and looking forward to coming back in the spring and doing some more work with this.
Let me say quickly too, Juan Etheridge is on the call. Thank you, Juan, for providing your facilities and the forward thinking to realize this is an important thing to be dabbling in. We appreciate you letting us use your data and your team to help pull this off.
No problem. I appreciate you guys because it's difficult trying to get management to understand the value of data unless you can show how you're going to get your good money out of it. And you guys are getting us closer to that end goal. So really appreciate you.
Good job, Caleb.
Yeah.
Like to make?
Well, I'm very impressed. We've gone all the way from a data detective to machine learning to spatial anchors, and it's been quite a journey. When I said sorry, I messed up your big reveal there, but I didn't ask any more questions. No, no, but really impressive, really is. I don't know, Jeff. Is there anything you want to say? You sound like you were a big part of this as well.
Oh yeah, thank you. I wish we had more time. I have a lot to say, but just yeah, for Caleb's work, this is huge. A huge step to spatially anchoring data data and analysis to really enable not just field workers here on Earth, but maybe astronauts on the moon in the future. So this is really a huge step for augmented reality and the work we're doing in IoT. But just a big thanks to all the interns and everyone who's been supporting this work all along. Dave Kelldorf, of course, Juan from the facility side. That we really appreciate it.
Yeah, and I want to echo something that Dave said. I mean, we started with this type of work 3 years ago, I think, with SND, wasn't it? And to see, Libby built on it, Caleb built on it, Gabe built on it, and so just the fact that these are continuation of work on top of everything, I think, is really important, and it's gonna cause us to go forward. So impressive. Thank you very much, and I look forward to everybody
See you next
continued
spring.
success. Yeah, that's it. Thank you.
Thank you.
Yeah.
Thank you, everyone.
Thanks, everyone. Great job.
At the second.